Welcome back, everyone. Before I announce our next speaker, I also want to announce a slight schedule change. You'll find this updated on the website soon, but tomorrow we had a gap in the 1:30 to 2:30 slot. We're going to move, excuse me, we had it on Wednesday, a gap, and now it's going to become a gap on Tuesday. Our chemistry hosts need this room tomorrow at that time. So we will be moving David Spire's talk from the so 1:30 to 2:30 tomorrow. It will move to 1:30 to 2:30 on Wednesday. And there will be a gap tomorrow. Okay, so we're really pleased to have from UC Davis, Eugene Gorsky is going to be telling us about generalized t-Catalan polynomials and link invariants. Eugene.
All right. Thank you so much. So it's great to be here. It's my first time in Minneapolis. It's a really beautiful city, and I think it's my second in-person conference after pandemic. So it's great to be here as well. So I'll talk about connection between combinatorics of this t-Catalan polynomials and t-Catalan numbers and some link invariants. And I can't. This, I guess. Fine. Oh. Go back. Yes. All right, now it's working. Sorry. So specifically, I'll be talking about an invariant called Khovanov-Rozansky homology. So it's a very complicated and very technical, let's say, invariant of links. I'll say a couple of words about it, but I'll definitely won't define what it is, and it doesn't matter. But I'll try to emphasize that there is a lot of interest in combinatorics in this homology. So even if you don't understand the definition, there are lots of interesting combinatorial equations which come out of it. And there are lots of interesting combinatorial answers, which we know. So this homology was defined in 2005, so more than 15 years ago. There were lots of results, lots of conjectures, which were proven like much recently, about 5 years ago. And I'll try to explain some examples of very explicit computations of Khovanov-Rozansky homology. What is the output of this thing? Some connections to t-Catalan combinatorics. A little bit about some general structures. What do we know about this homology? What we want to know about this homology? And then in the end, I'll talk about geometric models for some special classes of links. So this could be defined for any node or link, but for many interesting classes of nodes, you have actually much better understanding because there is a connection to algebraic geometry. So in many cases, you can basically build a variety, and the homology of this variety is Khovanov-Rozansky homology. And so in these cases, I'll try to explain briefly what is the variety, what do we know about this geometry, and then how does it help in understanding Khovanov-Rozansky homology. And it's been a long day, so I'll try to be not too technical in all this. So really, I want to show you some examples and like kind of general picture of what's going on. Okay, so all this starts with so-called HOMFLY-PT invariant or HOMFLY-PT polynomial. So it's an invariant of links, which is defined by skein relation, which is of course related to skein relations from previous talk. So if you have a link diagram, so for any link diagram, you associate a function of a and q of two variables. Generally, it's a rational function. It's a polynomial in a, but a rational function in q. And then, at least in some normalization, you can define it by local rules. So whenever I see a diagram with this piece, I can replace it by this piece or that piece. And the linear combination of invariants satisfy this relation. So if I have a diagram with the positive crossing or a negative crossing, the difference is actually equal to the invariant for the no crossing diagram with this factor of q minus q inverse. And then if I add a small loop or a small loop to the diagram, I get this factor of negative a inverse. And then if I have a closed circle, I can just remove it at the cost of this a minus a inverse over q minus q inverse. And then it's a classical fact that you can start from any link and then use these rules to simplify it to basically a bunch of unlinks and then recursively compute this invariant. So it's not so hard. It's a bit harder to prove that it doesn't matter how you simplify, you get the same thing. But again, it's very, very classical. And if you've seen a Jones polynomial by any chance, so if you plug in a is equal to q squared, you get the Jones polynomial in this picture. So this is a very, very explicit thing. And again, given any diagram, you can simplify it and compute recursively. And so what I will talk about is a generalization of this defined by Khovanov and Rozansky. So this is kind of a big and complicated machine, which again, I'm not going to define. But to any link, you define a triply graded vector space. So it's a vector space with 3 different gradings, I, J, and K. And I and J correspond to kind of variables A and Q in the HOMFLY polynomial. And the K degrees the homological grading on this homology, whatever this means. And so if I take the Euler characteristic with respect to this 3rd grading, I get back the HOMFLY polynomial. So specifically, if I take the generating function, Q to the I, A to the J, and then negative I to the K, so that's kind of the Euler characteristic part, I get a polynomial Q and A, and that is back the HOMFLY-PT polynomial. So that's kind of one of the defining properties of this Khovanov-Rozansky homology. But of course, you need much more work to actually construct this invariant, and that was very hard. And the definition uses Zorgel bimodules, it uses homology, it uses like really complicated homological algebra and things like this, and we won't need it at all. So I won't define it. That's like all what I want to say about this homology. It's some machine which I'm going to the black box, and I give you a link, and the output is a triply graded vector space. And what I want to understand is like, what are the dimension of these different graded components of this triply graded vector space? What's kind of the meaning of all this? Yes.
So, very basic question. That's a polynomial, but what was the previous slide of rational function?
That's right. So the question is, so P of AQ is generally a rational function. How do you get the rational function? So you get the power series in Q in general. So you expand this as a power series in Q. In each Q degree, you have a finite polynomial in A, and that's fine. And so this means that the homology will be infinite dimensional. And we'll see example of infinite dimensional homology in a few slides. Yes. But if we do combinatorics, so the answer is that for any knot, you can normalize things so that you have a finite polynomial. If you have a link with several components, it will be infinite dimensional. You kind of can't avoid it. So for knots, you can just do simple combinatorics. And then for links, you need to deal with these infinite dimensional things, but it's possible. And I'll show you some examples. Okay. More questions? Cool. All right. So here's an example, like as concrete as it could be. So on the left, you see the 3-4 torus knot. So what is the 3-4 torus knot? You take the surface of the torus and you draw a line with slope kind of 4/3. So you go 4 times around in this direction, 3 times around in this direction. And if you look at this knot, you can see the torus kind of inside and dividing. So that's pretty explicit. And so we plug in this knot into this magical machine of Khovanov-Rozansky homology, and the output is that. So this diagram. So I need to explain how to read this diagram. This diagram is from a paper of Gukov, Dunfield, L. Rasmussen, also around 2005, I think. So each dot represents a generator in this homology. So there are 5 dots on the bottom row, 5 dots on the next row, 1 dot on the top. So the total dimension of homology is 11. And then there are various numbers and various things. So the 2 directions on the plane represents the Q and A degree. So the horizontal direction is the Q degree. The vertical direction is the A degree. And these numbers that I put next to the dots are the 3rd homological degree, which I'm kind of ignoring. So again, it's kind of basic, stupid question is if you have a triply graded vector space, how do you actually visualize it? And there are various ways to visualize. That's one way, which works nicely in this example. And so, for example, if I take this guy here, so Q degree is 0, so the vertical axis of symmetry will be at Q is equal to 0. Then A degree is 6. That's what this says. So the bottom row of dots has A degree 6. Then you have 8, and then you have 10, I think. And then the T degree is 4. So the 3rd degree is 4. So anyway, some enumeration, maybe not the best one. But the most important thing is that the bottom row has 5 things. The next row has 5 things, and the top row has 1 thing. And then also there are arrows, which I'm not going to explain, but they're also very interesting. Okay, just to kind of put some suspense. But the arrows I won't define at all. Okay, and so one basic thing you can ask about the previous question is that, okay, you have 5, 5, and 1. Have you seen this 5, 5, and 1 before? And actually, all of you have seen this, I guess, more than I did. So this is like a very basic combinatorial question. How many diagonals, how many ways you can draw diagonals in a pentagon? And so there is 1 way to draw no diagonals. There are 5 ways to draw 1 diagonal. And there are 5 ways to draw 2 diagonals. So on the bottom, you'll have triangulations of the pentagon. There are 5 of them, and that's the Catalan number. And then on the higher levels, you have kind of partial triangulations. They are measured by some numbers. I think Creverus is the name. Narayana, I guess Creverus is whatever. So it's known how many of these are on every level. And so in this diagram, so one natural conjecture would be to say, well, maybe that's what it is. So maybe for each partial triangulation of a pentagon, there is a generator of this homology, which we don't know how to define. And there is some way to read all these complicated gradings just from these partial triangulations. And that's true. And so that was, so I have conjectured this basically looking at that example in 2010. And it was proven much later by Matt Hogenkamp and Anton Medit in 2017. And so here is the result. So the first statement is that you look at this Khovanov-Rozansky homology for a very special knot, n plus 1 torus knot. So n was 3 in the previous example. And the total dimension is the number of ways to draw non-intersecting diagonals in the n plus 2 GUN. So in particular, again, on the bottom level, you have all triangulations. That will be the Catalan number. The next level, you have like one less diagonal and so on. And on the very top, you have no diagonals at all. And so that would be just one-dimensional space on the very top degree. And that's kind of the total dimension, ignoring all the gradings. And then if you look at the bottom row, for example, of HOMFLY homology, there is a much more refined answer. So there are still two gradings on the bottom row, Q and T. And so by graded dimension, up to some regrading is equal to so-called t-Catalan number, which I'll define, I think, on the next slide. But it's known combinatorial object, which says like you have this, for example, triangulations. You also have dig paths, which are kind of easier to put statistics on. And then for each of them, you say, what is the Q grading? What is the T grading? And so that is precise kind of combinatorial encoding of this bottom row. And more generally, if you have any torus knot, again, there is a version which is called rational t-Catalan number. And I'll define it again on the next slide. And there is a way to put two statistics which measure things. And that gives the bottom row of this HOMFLY homology of the Mn torus knot. And so that works in general. It's very hard to resolve because this homology is very hard to compute. But these two gentlemen found a way to prove it. I will be saying mostly about the bottom row. So all the things extend to higher rows. Combinatorics is kind of trickier to phrase, but if you want, you can ask me in like draft formulas for all the rows as well. So it's like just all the complications you can see in the bottom row already. So I kind of restrict to that. Okay. So any questions so far? Okay. So then I need to define this t-Catalan numbers. And that's what happens here. So t-Catalan numbers have been studied by many, many people, starting from Garcia and Heyman, and also Francois Bergeron, Jim Haglund, and many, many other people. And so they can be defined in several ways. One way, which I personally like, is that you have m by n rectangle. So m and n parameterize the torus knot, and we assume that m and n are coprime integers. And you draw the diagonal in the m by n rectangle, and you look at all lattice paths below the diagonal, which don't cross the diagonal. So the total number of them is so-called rational Catalan number. If you would be in a square or n by n plus 1 square, or n by n plus 1 rectangle, that would be the classical Catalan number. And then there is some version for any rectangle. There is some formula for the number of such paths. Classically, so there is a bijection between the dig paths in the square and triangulations. And so here there are no triangulations, or actually maybe there are triangulations, and maybe Nathan will say something about this, but we won't use it. Instead, we want to just look at this path and say what are the two statistics which give us the Q and T degree on this path. So that's kind of what we're looking at on this bottom row. So the first statistic is easy. It's called the area. And this is the area between the dig path and the diagonal. So it's the number of whole squares which fit between the dig path and the diagonal. So in this case, there are 4 of these. So we don't count these squares because they're intersecting the diagonal. And these gray squares are wholly below the diagonal and above the dict path. Okay, so the area is 4. And so you can definitely weight all the dict paths with area. And then the next statistic is more complicated. It can be defined in several ways. That's probably the most economic and least understandable, I'd say. So we zoom in into this rectangle and the dict path, and we look at every box of the Yann diagram below the dict path. So for this box, I can define the arm and the length, and I'm looking at all boxes. Well, roughly speaking, the ratio of arm to length is very close to m over n. And more specifically, I take the arm over leg plus 1. It's less than m over n, and it's m over n is less than the arm plus 1 over leg. So arm over leg plus 1 is really, really close to m over n. And then you count such things. So the total number of such things is dinf. And that is some kind of very strange statistic, which is very different from area and everything that we've seen before. And again, there are many, many different definitions of these statistics. Okay. And then the t-Catalan number is just the sum of over all dict paths, over all these paths below the diagonal of q to the area and t to the dinf. So this is the generating function that we write here. And so in this sense, so the theorem from a couple of slides before says that you can find a basis in this Khovanov-Rozansky homology where the basis vectors are labeled by this dict path, and the grading of a basis vector is given by the area and the dinf of the dict path. So that's what it says. And it's kind of, there are so many questions about this, and it's kind of a separate talk on its own just to talk about these t-Catalan numbers. But I just want to mention this theorem that Anton made it proved also around 17, I think, following my work with Andrei Negutz and work of Bergeron, Garcia, Levin, and Sin, that you have a different formula for t-Catalan number, which has very, very different flavor. And namely, you take all standard Yann tableau of size n. For each standard Yann tableau, you compute the QD contents of boxes labeled by every I. Maybe I won't define it, but it's like easy to define. And then you put all this into this big giant rational function. So it's a product of 1 minus the over zj, while qt is the over zj, and so on. And then here, so all this depends only on n, because we take standard Yann's tableau of size n. And then here, you put a monomial in these. And the exponents in this monomial are the strange things. So you take integer part or seeding of im over n minus the seeding of I minus 1 m over n. And so that is like the only place where you remember m. And you take this giant sum. So all these terms will be very complicated rational functions in Q and C. You sum all them up, and then suddenly the sum of these very complicated rational functions is a polynomial in Q and C with non-negative coefficients, because that is our t-Catalan number. That's this positive sum over the dict path. So this is really, I think, very interesting identity. So for usual Catalan numbers, it was proven before by, again, Garcia and Heyman in Haglund. But in this rational case, it's actually much harder to prove, and the structure is more complicated. So this was much later by Mellet. And there are lots of interesting consequences from this formula. So one consequence is that the right-hand side is manifestly symmetric in Q and C. And so if we believe in this formula, then the left-hand side is manifestly symmetric in Q and C. And that's not obvious at all, because the area and dinf have very different definitions. And it's a very hard combinatorial question to actually prove it kind of bijectively that the area and dinf have the same distribution or the same common distribution. The right-hand side, on the other hand, is a polynomial in Q and C, which is also not obvious because it's a giant sum of rational functions. Yes? So the left, yeah, so the first one, let's say, is the definition of CMN. So this is the definition of CMN of QT, and this is the formula for that. I mean, you can take the second to be a definition, the first to be the formula, but your theorem is that they're all the same. So it's fine. Right, and both of them compute the invariant of this torus knot. Again, so the right hand side is a polynomial in QT. Well, that you can actually prove by combinatorial methods. The fact that this is polynomial with non-negative coefficients is much harder. And then it's a funny fact that the right hand side is symmetric in M and N, which is also not obvious because you take standard tableau size N, M appears only in this like weird exponents. But the left hand side is manifestly symmetric in M and N because you take this M by N rectangle, everything is symmetric by M and N. And so there is a lot in here. And again, there is a huge body of literature around t-Catalan numbers, which I'm not going to discuss more. Yes? Huh? Say it again? Yes. I didn't define these, but these are QT contents of boxes. I can actually define it. That's fine. So I can say, so if you have a diagram like this, so you put, and let's say you have 1, 2, 3, 4, 5. So you're saying that Z1 is 1, Z2 is, let's say, T, Z3 is Q, Z4 is QT, and Z5 is T squared. Okay? And then you can guess what's the general formula for this Z's. Okay? Yeah, so the question was, what are the Z's? These are the Z's. And so you just look basically, so goes in this direction and T goes in that direction. And then you count monomials like this. Yes. I think I broke some. Okay. Yes.
So is this an open problem to find the other curve statistics?
Yeah, I think so. I think so. Yeah, so the question is like, I mean, can you find another pair of statistics which is symmetric in QNT? Yeah, that's an awesome question. I don't know the answer. I think it's an open problem. Another open, like very hard open problem, which many people thought about, like in particular, I think Nick Lure and Jim Haglund, is like, can you find a bijection which exchanges area and din? Like that would be awesome. That's very hard question. Easier question, which is actually known, is that the area and din separately are equidistributed. There are various combinatorial ways to prove it, and I'm not going into that. Okay. All right. Yeah. So there are lots of, I mean, there are lots of facts here which are kind of known, but there are lots of questions which are not unknown. Okay. And then to get on with these t-Catalans, so I just want to remark that in principle you can write the right hand side for arbitrary d's and ask what's going on if you have arbitrary d's on the right hand side. So maybe there are, let's say all of them are positive, fine. But like bigger sequence of positive numbers on the right, you get some expression. And that expression again is manifestly symmetric in QNT. Experimentally, you can see that it's positive in many cases besides like this particular case. And you can ask what's going on. And that's my next slide. Yeah, so maybe I'll read the problem first. So you can define generalized t-Catalan numbers by exactly the same formula with z's and stuff, but the exponents d1 through dn are arbitrary. And the question is, do you get a non-negative expressions? In many cases, yes. Conjecturally, for if d1, if the sequence of d's is non-strictly decreasing, then you get non-negative coefficients, and that's you can see like experimentally. You know how many terms are there, and these are parameterized by certain Young diagrams. You can cook up the area statistic, but like nobody knows what the dim. So I think that is a very good open problem to find what's going on in this case. And again, it's very easy to just go to this formula, program it, and then say, well, this produces some sequence of polynomials in QNT, which are symmetric in QNT, and quite often positive. What do they actually mean combinatorially? And just to finish, and then I'll answer your question. So there are a few things here. So they are related to Homology homology of certain knots conjecturally, and I can explain which knots are these correspond to, but maybe for this audience, it doesn't matter that much. For small cases, I think for n less than or equal to 4, We had a paper with Anna Schilling and Graham Hawkes and Julian Rundbold, where we proved that this has no negative coefficient and it's QT symmetric combinatorially, but it's kind of really ad hoc and like it's not clear how to generalize to any bigger example. And then very recently there was a paper of Blasiak, Heyman, Morse, Spahn, and Sillinger, when they proved that for slightly more general example that this thing when you have pass below some certain line. And I don't want to explain the details, but there are some cases known, but most of it is unknown. And just to finish with this, so again, t-Catalan numbers are related to lots of other things, combinatorics of Montgomery polynomials, shuffle conjecture, Hilbert scheme of points on the plane, representation theory of double affine K algebra, elliptic hole algebra. And again, like if you're a combinatorist, if you don't care about all this stuff, like there are many interesting ways to compute this thing. And comparing them leads to identities like we've seen on the previous slide. Yes? So someone had a question here. David? No?
I was going to ask about whether it was clear if it was polynomial.
Say it again?
I was going to ask whether it was clear if it was polynomial.
Yes, it is clear that this is a polynomial. Yeah, so the question is if the right-hand side is a polynomial for arbitrary d's, yes, the answer is yes. You can rewrite it using some contour integrals as like a giant sum over giant things, which will be polynomial, but it's kind of, that would involve a lot of cancellation. So the fact that you have non-negative terms is not obvious at all. Yes? So you can choose arbitrary d1 through dn. So for torus knots, you need to choose d1 through dn's, which are this numbers over here on the bottom. But you can change the problem and say, what about arbitrary d1 through dn? That gives you something on the right-hand side, but there is no left-hand side to compare it to. So I think that's my question. So this formula is defined for arbitrary d1 through dn. This formula makes no sense for arbitrary d1 through dn, and the question is, what is the analog of the left-hand side for arbitrary d1 through dn? Yeah. Yes. Yeah, so experimentally, at least if d's are decreasing, it's always positive, and you know how many terms are there. That's you can compute what is the specialization if q is equal to t is equal to 1. So that you can separately compute. Okay, right. So that was about this generalized q-Catalan numbers, and again, like there are very special knots which correspond to this. And again, like if you're into examples, there are few other classes of knots with known forms like homology, in particular two-bridge knots, which are parameterized by rational numbers, not defining them. And maybe I want to advertise this recent work of Nakagane and Sana, who actually computed homology homology from definition, just very complicated complexes, and they made some very tricky simplifications of them. And this works for all knots with at most 10 crossings, most 11 crossing knots, and there are a few hundred of knots where they know not homology homology. Most of them are not torus knots. And the question is like, what's combinatorial interpretation of that? So you can build a table, you can study the numbers. They're all very interested. And I think there is a lot to be explored in this direction. Okay. So this is about examples. I think that's all what I wanted to say about examples. And then the question is, can we kind of look at these examples and guess some general structures that we have? And the first structure, which took very long time to prove, so it was conjectured in the same paper of Gulkov, Dunfield, and Rasmussen in 2005. And we only proved it last year with Matt Hogenkamp and Anton Mellet, is that this picture is definitely symmetric. So there is a vertical axis of symmetry of this picture. And the statement is that for any knot, absolutely any knot, this homology homology is actually symmetric around the vertical axis with appropriate definition of vertical axis. And moreover, there is an action of Lie algebra SL2 in homology homology. And any finite dimensional representation of SL2 is symmetric, and so that is this symmetry. And so this SL2 is kind of visible here because you go from here to here, from here you jump to here, and then to here. So that's one SL2 chain. And then this guy sits on its own on a separate SL2 chain. And so the action of SL2 preserves these layers, preserves these levels. And then you have interesting SL2 representations that we can study there. And you can say what SL2 does to all these degrees, but that's not so important. And then separately, for some class of knots, maybe for all knots, the similar result was obtained by Galash and Lam, and I think Pavel will mention this tomorrow, and also by Oblomkov-Rozansky. But the technique that they used was very, very different, and like really complicated geometric representation theory, and we used kind of more elementary techniques, but in very different ways. Anyway, so the statement is that at least they have some structure and is symmetric. And if you go back to t-Catalans, in particular, this symmetry is just the symmetry between Q and T that I was talking about. That if you know that theorem about the symmetry, this means that, and you know that t-Catalan is not homology, kind of a posteriori, you get that t-Catalan is symmetric. Of course, this is kind of very hard way to prove the symmetry, but it shows that the symmetry is very non-trivial because it leads to this very non-trivial combinatorial identity. You can also ask what happens for links with several components. And so David asked when you get a rational function. And the HOMFLY polynomial is a rational function. The HOMFLY homology is infinite dimensional. And in particular, it's a module over some big polynomial ring when you have one variable per component of your link. So that's pretty big. And there is no way to define a symmetry for links which preserve this action of variables. It's just like the degrees of these variables are not preserved. And so Matt Hogenkamp and I actually defined a deformation, so-called yfication of HOMFLY homology. So a slightly enhanced version, which is the same thing for knots, but slightly different thing for links. And it depends on additional variables y1 through yr. And actually in this paper with Matt and Anton, we proved a more general thing that yified homology, this kind of deformed homology, is always symmetric for any link, and the symmetry would exchange x variables and y variables. But you need to introduce these additional variables to even make sense of this symmetry. Okay, and since we're talking about links, I want to give one example, which I think is interesting on its own from many points of view. So this is n torus link. So I have n components. All these components are unknowns, but all of them are pairwise linked with kind of the simplest link in pattern 1. And this is a link with n components. You can ask, what is the answer? What is this homology? And so the homology, you can kind of compute combinatorially what it is. It's kind of messy, but it's known. And there are some recursive formula for this. There are some kind of Dean formula for this. But there is actually a better answer, I'd say, from the viewpoint of commutative algebra, because you have all these variables. And so you have variables x1 through xn, y1 through yn. And the answer is the ideal in the polynomial ring in x's and y's. And so this is the intersection of ideals generated by xi minus xj and y minus yj for all I not equal to j. And so you can think of it geometrically as you have C2 to the n. So you have n points on C2 with coordinates x1, y1, x2, y2, x3, y3, and so on. And you look at the diagonals in there where i's point and j's points collide. So defining ideal for one such diagonal is precisely this thing, xi minus xj and y minus yj. And then if you have the ideal for the union of these planes, this is the intersection of ideals, and that is what this thing is. So you can really think of it as the ideal for the union of all diagonals. And this is the yified homology. So in particular, the symmetry between x's and y's is really visible here because everything is symmetric. And if you want the non-yified homology, the usual one, you just quotient by y's. So this thing is secretly free over y's. So it's not free over x's and y's, but it's free separately over y's. And you can quotient by y's, and that's kind of the usual Khovanov-Rozansky homology. And again, like in principle, you can write a combinatorial formula for this related to this DINF and other statistics. And there was a separate paper of Elias and Hogenkamp when they do this, but this you can prove directly without the combinatorial formula. So this is kind of a different approach, but also I think interesting. So sometimes you can get an answer like this, even though maybe you don't see immediately like what's the HOMFLY polynomial or HOMFLY homology, but commutative algebra helps you. And again, this like you can study this as a module over x's and y's. You can study its resolution and lots of other things. And again, yeah, I think that's all. All right. Yes, and so I want to switch things a little bit and talk a bit about geometric models. So we saw some examples of computations of forms like homology. Can we see any of them from geometry? Like is there some variety, maybe algebraic variety, topological space, whose homology is related to this knot homology. And the first easiest to define model is given by so-called Braid varieties. So the Braid group on n strands has generators sigma 1 through sigma n minus 1, and the Braid relations, which I think many people here know. And for any generator, you put a matrix of this form. So you have 0, 1, 1z at ith and I plus first position, and ones everywhere else, and zeros everywhere else. So these matrices satisfy this condition that bi of z1, bi plus 1 of z2, bi of z3, and you can't see that, I'm sorry. Can I move it? Oh, yeah. Yeah. So on the left-hand side, you have I plus 1, and I. And the variable size z1, z2, z3. On the right-hand side, you have I plus 1, I, and I plus 1. So that's like the Braid relation. But there is some change of variables which happens. So z3 becomes z1, z1 becomes z3, and then in the middle, you have z2 minus z1, z3. Okay? So this is just some matrix identity which you can verify. And this means that if I have arbitrary Braid, I can put a variable for every generator of the Braid group. And if I start changing the Braid, the thing would change, but up to this change of variables, they won't change. And so more precisely, okay, now I move this, okay. You can define the so-called Braid variety as following. So for every generator, so you have a Braid, sigma I1 up to sigma k. You replace this generator by bi of some variable z. So you have one variable for each crossing in your Braid. And then you take the product of these matrices, and then by some technical reason, you put this matrix where you have one on kind of the opposite diagonal. And you require that the product of all such matrices is upper triangle. And I didn't put all the references here, but like these varieties appeared, I guess, first in the work of Deline and other people. I think Anton Melit popularized them, at least to me. And so he has several papers about them. And then we wrote a couple of papers with Roger Casals, my brother Michael, and Jose Cimental. And kind of one very basic question which you can ask about them is like, what can we say about this variety? And it turns out that it's either empty or it is a smooth manifold of dimension, the number of crossings in a Braid minus n choose 2. And if the Braid closes to a knot, then actually you can factor out some torus, you start to some power, and that's a free action. Maybe I should also mention Laura Escobar here. So she also considered like very, very closely related varieties. But fine, okay? And then the big theorem here is that, so you define this algebraic variety, it's very, very explicit. I'll have example on the next slide. And then you just take the usual homology of this variety, and that recovers the Homfly homology. So this goes back in some form to Webster and Williamson, although they didn't use this notion, and then very explicitly. It's not working? Yeah, sorry. That's better? Yeah. So if your Braid closes to a knot, and then you have homology of this variety, that is actually the same as Homfly homology, although you need to explain what are the gradings. So one of the grading is homological grading, and another is so-called weight filtration, which is very complicated. And so, as I said, so this goes back to Webster and Williamson, then work of Anton, and then in very kind of rigorous and precise way, it was written in a paper by Min Tam Trinh. And yes, you can put the half twist, and I'm kind of, yes. There is a bit of a lie here, but I don't want to correct. Yeah, the Braid is positive. That's the most important thing, that this only works for positive braids. Yes. I'd say the Braid is positive, not containing the half twist, but again, it's kind of whatever. So you can take any positive braid here, actually. And so this computes the homology not of the closure of this braid, but the closure of this braid with negative half twist, actually. So you get a little bit more than just positive braid. But it's technical, and I don't want to explain it. But I can answer later, okay? So yeah, you have a big class of braids here. And then, yeah, so here's one concrete example. So if I start from a braid sigma cube, that's the variety that I get. So yeah, Z1, so you have three variables, Z1, Z2, Z3, and the equation is that Z1 plus Z3 plus Z1, Z2, Z3 is 1. And it just follows from this kind of matrices and then multiplying all these matrices and checking that the product of matrices of 2 by 2 matrices is upper triangular. So it's very, very easy condition. So this is a very, very easy algebraic variety. And then you take homology of this variety, and then it turns out to compute the invariant of the trefoil knot, for example. So that's good. And then kind of in this direction, there is a beautiful result of Pavel and Thomas of Galash and Lam that if you start from a torus knot, you can actually identify this variety. So I'll rephrase like the result as follows. So this braid variety is exactly the same as the open positoroid variety in Grassmannian M n plus M. So this is some open subset in the Grassmannian defined by non-vanishing of cyclically consecutive minors. And this homology may be quotient by some torus, which I'm skipping as well, equipped with wave filtration is given by t-Catalan numbers Cmn of Qt. And I'm sure Pavel will talk more about this tomorrow, so we can address all the questions to him. But one thing which I want to mention, though, is that so the way they prove it, basically they say that the homology of this variety is the same as not homology, and then they refer to this work of Anton. So kind of, I think a big open question here, which I should have put on the slide, is that how to compute this homology without knowing not homology, like geometrically. So the only proof that is known to the moment is actually going to the not homology, using this complicated work of Hogenkamp and Mellet and others, and using the results there. But somehow, can we reprove these results by geometric means? I think it's an excellent question, and I don't know the answer. Maybe Pavel and Anton know, but I don't. But I think this is like very, very explicit variety, which you can define for any M and N. And the answer is given by these t-Catalans, which are complicated by what we said. Can we find the basis in the homology labeled by Dickpath? Can we find like any of that? I think that's a very, very good question. Okay, so that's about this braid varieties. And again, you can define it for any positive braid. And there are lots of examples where the homology is kind of more complicated. You have odd. So in this example, you have only even dimensional homology, and that's why you have pluses in the t-Catalan. There are many examples where you have odd dimensional homology that would give you minuses if you kind of naively do the computation. And then there are lots of questions about this, like what can you say for other braids? What can you say for like other classes? But I think just understanding the geometry is a very interesting question. And maybe before I go, so there was this example of 3-4, which I mentioned before and drew this diagram. So this is known as E6 cluster variety. And for this variety, there was a separate work of Lam and Speyer where they actually computed the homology of this variety using cluster theory methods. And they got the same results, so they got the same 5, but kind of, so for that case, the answer is actually known, but it's kind of very, very different computation. And again, understanding what's going on is like nice open problem. Okay, right. So there are 2 more geometric models which are harder to define, but actually easier to compute in many cases. And I'll just briefly say what they are. So the second geometric model is given by so-called Finespring fibers. So they depend on an n by n matrix, gamma of t, which is a matrix dependent on one single parameter t. So that's an example of such matrix. And here's the definition. So you take the vector space of power series valued in Cn, or like a vector space over Laurent series in T. Subspaces, which are invariant under the action of T and under the action of this matrix gamma of T. So there are a lot of research about the Finespring fiber in geometric representation theory, and I'm not going to talk about any of this, but where is the knot in question? So to any such gamma of t, you can write the characteristic polynomial. It would depend on now two parameters because the matrix depended on t, and you have kind of eigenvalue parameter y. So in particular, if you compute the characteristic polynomial of this matrix, it will be y squared minus t cubed. So this would define an algebraic curve on the plane. And if you take a small neighborhood of the origin, so this is C2, it's 4-dimensional. If you take small neighborhood of the origin intersect with this curve, it's kind of hard to explain in 1 minute, but this intersection will be a knot. It's so-called algebraic knot. In this case, it will be just 2-3 torus knot or the trefoil. Okay, and so for any gamma of t, the point is that you have some algebraic variety, which I didn't properly define, which is called the Finespring fiber, and then you have a knot, which is the knot associated to the corresponding algebraic curve. And so in particular, if you take this matrix, you get the curve y to the n is minus t to the m, and then it's easy to see that corresponds to a torus knot. And one thing which we proved about 10 years ago with Misha Mason is that for such gamma, you can actually compute the homology for Finespring fiber, and it agrees with the t-Catalan number. So I need to explain, I don't want to explain what's the second grading. There is a way to put a second grading on it, and then you can basically pave this variety by find cells, count dimension of cells, and then the dimension of the cells matches this complicated Dean statistics that I was mentioning before. And so in this case, you can actually go ahead and compute homology geometrically because you have the cell decomposition. So for 2-3 example, you have P1, and you know how to compute homology of P1. In the more complicated examples, you have more complicated varieties, but for all torus nodes, this is actually doable. You can count cells, and you know the dimension of the cells. And that kind of explains the geometry behind this weird Dean statistic. And there is of course, this was motivated by more general conjecture of Oblomkov, Rasmussen, and Schende that if gamma of t satisfies some mild assumption, it's always true that the homology of a Finespring fiber is isomorphic to HOMFLY homology of the link. And as far as I know, this conjecture is wide open for all cases which are not torus knots. And it would be very interesting to compute some examples and see if that works in like. So there are some other examples where people know homology for Finespring fiber. I don't think in that case we know HOMFLY homology, but there are lots of questions out there here. And that's kind of brief, but I want to say that like there is a different geometric model where you can actually compute homology directly without any trickery. And then the third geometric model is very complicated. And it's given by the Hilbert scheme of points on the plane. So you can think of this as you take n points on the plane, you look at all unordered tuples of n points on the plane. So this is this quotient of C2 to the n mod Sn. This is a very singular space, and the resolution of singularities is called the Hilbert scheme of points on the plane. And so given a braid, one expects a vector bundle or coherent sheaf on this space. And the space of sections is expected to match the HOMFLY homology. So this is a very, very different model. It's not homology of a space. It's rather space of sections of some vector bundle. And the two gradings correspond to the scaling action of C star square on the Hilbert scheme. So you have an action on C2, you have an action on the Hilbert scheme. And again, I'm not going to any details. And there are several constructions of this sheaf in my work with Nigut and Rasmussen, with Hogenkamp, and there's a very different but very general construction for arbitrary beta, how to do this by Oblomkov and Rozansky using like lots of heavy machinery. And I mean, all this kind of makes no sense and looks very complicated, but I want to give two examples which are motivating for like this particular question. And so one example is nn plus 1 torus knot, or 3-4, for example, which kind of where I started with. So in this case, you actually know the sheaf, and this is just the line bundle on the punctual Hilbert scheme on the plane. And that was studied much earlier by Mark Heyman, and he computed that the dimension of the space of sections is given by t-Catalan number, by the classical one. And so in this case, you can actually compute everything, and again, it matches up. And actually, this complicated formula with standard tableau and z's and things, you can think of some kind of localization, IT-board localization for computing the space of sections in this case. And I'm not explaining that. And then the second example where I have NN torus link, this is again some complicated vector bundle on the Hilbert scheme. And again, by the work of Heyman, the space of sections is this intersection of ideals, or the ideal of the union of diagonals. So the Hilbert scheme is very closely related to a blow up of C2 to the n in this union of diagonals, and that's why it appears. And so there is a lot of interesting kind of commutative algebra and algebraic geometry coming from these examples, and they can be generalized and used to study these things. So kind of, I'd say that this third geometric model, I mean, it might be hard because like in practice, we know these examples, we know a few other examples, and it's kind of hard to say, but you can study lots of properties of homology based on this, in particular, how adding a full twist to a braid changes the homology. So that's very clear in this setup. And I think that's all what I want to say. So for more references, so there is this paper with Matt and Anton about symmetry and tautological classes. There is a review paper with lots and lots of references. We try to put like as many references as possible with Oscar Khovanov and Jose Cimental, algebra and geometry of link homology. And like all these things that I talked about, all these examples are definitely there with like precise references, what is proven, what is conjectural, and so on. Again, I want to advertise this paper of Nakagane and Sano, and the code that they wrote and the kind of output of the code they produced, computations of homology homology when they have like very, very explicit answers. And then for generalized t-Catalans, there is a discussion in this paper with Fox, Anna Schilling, and Julian Reinbold. So, and yeah, I would be happy to talk more, and I think that's it. Thank you so much.
Okay, so as usual, questions from the room first, questions in the chat later. Any questions in the room for Eugene? Yeah.
Early on, you mentioned how you showed the big parts with other numbers. Should the rows be defined again numbers?
Yes.
And instead at the end, that of course is not a problem. Try to find the base, but easily by identifying.
Yes.
But can you do the in between and find through the concept polynomial something that corresponds all of the big parts with a given number of peaks?
Yes.
Although the big parts with a given partition of the parts.
Yeah, that's exactly right. So like, so these higher levels, they correspond. So they either correspond to partial triangulation or this path where you mark some of these peaks here, I think. So you can phrase it like this. And then for such path, you have a version of the Dean statistic. And so you can compute it, but I don't think it's easier. So you can define this whole thing together and define Dean statistic on that. So this gives you kind of generalization, further generalization of t-Catalan numbers. There is kind of uniform version, which is related to parking functions, which many people study, and I don't know, some people might mention, maybe. But anyway, so you can put some kind of integers here so that they decrease on vertical runs. And so there will be some SN representation by these generalized parking functions. And for parking functions, you can define the Dean and the area and this kind of QT version of parking function. So this would give you bi-graded SN representation. And you can extract all this from that. So that's kind of the biggest thing possible. And I think it's like from knot theory perspective, you expect some interesting SN representation, but it's kind of technical. From some of these geometric models, you get this SN representation for free, and you get the same thing. So in particular, this identity over here, this can be identity of symmetric functions. So there is kind of much bigger identity of symmetric functions, which precisely says that instead of counting summing over dig paths on the left-hand side, you sum over parking functions. And there are some statistics, and there is some kind of symmetric function going on. And on the right hand side, you take exactly the same formula and you just multiply by Macdonald polynomial. And then you sum up. And so that is what is called rational shuffle conjecture. That's what actually Anton proved. So there is this generalized symmetric function version of this. And like all the statements, presumably there is a symmetric function version. It's kind of harder to work with. And again, a knot here is like not completely defined, I'd say. But like some things are defined and just harder, in my opinion. But there is kind of underlying symmetric function for all of this. Yes. Yes. Not directly.
Can you repeat it, Eugene?
Yeah, the question is, so you have Tat polynomial for some graphs, and like, can you define what is the relation between HOMFLY polynomial and Tat polynomial? I don't know that well. Tamas Kalman has several papers about this relation of HOMFLY polynomial, Tat polynomial, and also relation to this actually Braid varieties, because he was counting points in Braid varieties, and that's related to some of these things actually. So he had. I don't know, but I don't see the Tat polynomial here. But I mean, it's a good question, but I don't know. Yeah, but I think like Tamas has some results in this direction. Yes, Eva. Yes, for this generalized, when you put arbitrary d's here. Yeah, so the question is, put arbitrary d's here, what's the knot? And so in the Braid group, you have this guys which are, let's say like this. So you take, let's say the first strand, you go around the first I strand, and then you come back. Maybe I want to do it here actually. So these things, let's call this Li, so they all commute in the Braid group, if I draw them correctly. Yeah, I think I drew them correctly. So this is a large commutative subgroup in the Braid group, and you just put the product of this Li to the power di. So, and then you close up so that you actually get a knot. But yeah, roughly speaking, you get just the product of Li to the power di. That's right.
Other questions in the room? Other chat? No chat questions. All right, let's thank Eugene one more time.